Hi everyone, welcome back to the Coding and Analysis YouTube channel. And then today we're going to create our function train and predict using the XGBoostRegressor. So the code builds a position specific XGBoost regression model for the running backs, wide receiver, tight ends, and the quarterbacks to predict the 2025 PPR points using the historical player stats and health data and other information like projected roles. It trains, evaluates, and outputs predictions for each player. So when we do here, we start off with train and predict, and then these are the parameters that we're going to use in our function. So the combined stats is the original data frame. So what we're doing here is we're making a new data frame, so called position_data, and this filters the data to only include players at the specific position. So we'll have all the players, we'll have all the running backs first, all the wide receivers and tight ends second, and then last we'll have all the quarterbacks. Third, I'll have them neatly filtered and aligned by the same position until it changes, until the position changes. And then the dot copy ensures we're working with a new data frame and not a view. So we always want to make a copy of our, we don't want to use the original data frame, which was combined stats. And then we do our handle empty position. So if we safely check to avoid downstream errors, no data is found for a given position. But for the most part, all the data is for the positions. All the players have a position in that column. So each one, there's no player missing, a wide receiver, tight end, running back, or QB. They're all there. So we're not going to get any errors. And then for the feature and target definition, the X contains the independent variables or predictors that we're going to use. And the Y is the dependent variable or target variable, which is the 2025 ESPN PPR points. And then the dot fill NA0 ensures the model won't crash due to missing values. But we don't have any missing values in PPR. And the features, if there are, it'll just change to 0, so that won't be an issue. And then we reset the index, so that's going to align the index across X and Y in the original data for safe splitting and mapping later. So we're just resetting the indexes for alignment, making sure the alignment is correct for all of the X and Y and the original data. And then the train and test split with index preservation. So right here we're doing the 80-20 split on the data set for train and testing, and then also retrieves the original data frame indices. So that's going to be called the position_data.index to tag data later as train or test. So that's how we'll be able to note whether the player is in a train or test group. And then right here, so we add a column to indicate which rows are train and test. So marks each row in the original data as part of the train or test split. And then that's going to be useful for evaluation and visualization that we're going to use. And then here's where we're going to get the initialize, train, and test the XGBoostRegressor model. So we're just going to call it XGB as the abbreviation, but it's really the XGBoostRegressor from up here that we imported from the XGBoost library. So we have bunch of different parameters, number of estimators, max depth, learning rate, subsample, column sample, underscore binode, regularization alpha, and regularization lambda. Then the random state for reproducibility. So the number of estimators is going to be 150. So we're building an ensemble of 150 decision trees. Each tree tries to connect the errors of the previous one. So why this is important, more trees can lead to better input performance, but too many can cause overfitting. The model memorizes noise. So that's why we don't, we have like 286 players in the data set, so that's why we don't want to use 200, 250, because we don't want overfitting to occur. And then the max depth, so we have equal as 2. So each tree in the model can grow only 2 levels deep. So shallow trees like depth of 2 are simple and less prone to overfitting. So this setting encourages weak learners, which work better together in boosting. So just really think of it as shallow trees to reduce overfitting. So that's what we want to avoid for the most part, is overfitting. And then the learning rate is 0.1, which is also called ETA and XGBoost. It scales the contribution of each tree. Smaller values make the model learn more slowly and carefully. So what this does is going to help improve generalization. You can often use a lower learning rate with more trees to achieve a better performance. So control step size shrinkage. So that's why we're using the lower rate of 0.1. And then the subsample, we have it as 0.8. So each tree is trained on a random 80% subset of the training data. And fraction of training samples used per tree. So it's going to be 80%. And then the column sample underscore binode. So at each split decision in a tree, the XGBoost randomly samples 80% of the features. And this is also going to help prevent overfitting by reducing reliance on any single features. So it adds randomness like subsample, but at a feature level. So we have the subsample as the randomness of the 80% subset of the training data. So the column sample by node is where it's going to kind of reduce reliance on any single feature from these feature columns that we've talked about in the previous videos. So then the regularization alpha, or L1 regularization. So this adds a penalty for using too many features. So encourages sparse solutions, pushing feature weights to exactly 0. And then what this does is it helps with feature selection and simplifying the model, especially useful when you have many correlated features. So features might have like, how many features do I have? So like 17 features. So what this alpha, I guess, is trying to do is it's pushing feature weights to exactly 0. So I'll have to see which of those features that I just saw in the 17 that those columns are put to 0. So I'll remember to look at that. And then the L2 regularization, or regularization underscore lambda. So we have that equals 1. So it adds a penalty for large feature weights. Tries to shrink all coefficients without pushing them to 0, like ridge regression. So one thing to look up for regularization alpha is lasso regression, and then for regularization lambda is ridge regression. So for this lambda, by doing a penalty for the large feature weights, it helps reduce variance and overfitting, preventing the model from relying too heavily on a few specific features like the projected roll. I know the projected roll was like 50% of the quarterback, so it'd be interesting to see if it's still, the feature importance is still using 50% for that. And the random state, the random number generator seed, so that the model's randomness from sampling the rows and the columns is reproducible. So it ensures we get the same results each time when we train the model. And then we train the model right here with the alias XGB.fit, and then this .fit method right here, so it fits the model on the training set using the selected features and targets. So these are all the feature importances right here. This is our targeted ESPN, PPR, and then we do the predict on train and test. So this is going to generate the predicted 2025 PPR points for both training and test sets. So you can see here the X and the X. So these are our feature columns, and we're going to name it. You name it Y underscore pred underscore train, Y underscore pred underscore test, and then we evaluate the models using the training MAE, using the so ESPN's model, our model. So ESPN's model, our testing model. So our training model, our testing model results. And so we're going to print that out, and then we're also going to print out the feature importances. The most important one is going to be at the top, the least going to be at the bottom. So we'll see if using the setup as 0.1 to 1, if there'll be any differences in the feature importances. And then the predict all players. So the position underscore data frame, and then we're really creating a new column in this data frame. So we're creating this column, predicted fantasy points, and then we're saying xgb.predict x. So we predict the fantasy points for the full dataset train and test. So we're just adding a column for model predictions for all the players. And then we're returning the output right here. So this will be the end of our function, our train and predict function. And then we start bringing in our parameters, the features that we had for the previous videos. Let's see if I think they're all the same. Got projected roll and adjusted risk is in there as well for all of them. I think the wide receivers, the tight ends, and the running backs, they all have the same features. Just the quarterback features are different, a little bit different. We're not including receiving yards. And then we combine all of the position results and round to 2 decimal places. So we're doing concatenation right here. And so the running backs will be first, wide receivers, tight ends will be second, quarterbacks will be third, rounding to 2. And then this is the override dictionary that we're going to use. So it's going to be an update. The previous videos, I just had Tank Dell, but Mike Williams, he retired, and Will Levis will be out for this season. So I updated those 2 players. So we've doing a for loop to go through this to tell our model, to tell our results, to input these into the results. So then we're exporting the results to the CSV file, and then this is the output path that we're using. And then this was going to show up in the CSV file. So the predicted fantasy points that we made up here, this column, and then the ESPN model. And you can see here the MAE results. 6.9 for the training. Testing is a MAE, but I'll do that in the next video. I think this video's getting too long, so I'll do that next video. I'll go over the results, look at the CSV file. So see y'all in the next video. Bye. Thanks for watching.